Okay, thank you so much for the introduction. My name is Robert, and today I'm going to tell you about recent advances in predicting properties of quantum many-body systems. The first part of the talk would be our original work published last year at Nature Physics with Richard Kuhn and John Preskill. And in the second part of the talk, I will discuss several recent works that build upon our formalism called the classical shadow formalism. So the main motivation for this work is to understand how one can construct an accurate classical representation of a many-body quantum system efficiently. So imagine that in the experimental lab or in some physical setting, you have encountered some unknown quantum system. So maybe you fabricate it in your lab, and now what you wanted to do is you wanted to construct an efficient classical representation of this unknown quantum system such that you can predict a wide range of different properties of the original quantum system. So why do we want to do that? So first, the main motivation is, of course, to understand what this physical system is. For example, it might be some material, it might be an analog quantum simulator, it might just be an array of Rydberg atoms. And you just wanted to know what kind of properties does your physical system is and what have you constructed. So since we're a classical being, in order to understand what this quantum system is, we have to construct a classical representation of it so that we can reason about it, so that we can better control our system, or we can better improve upon this quantum system. Another important motivation for considering this task is that a lot of recent quantum applications, there are much more near-term, like near-term quantum applications, rely on this thing called the hybrid classical quantum algorithms, where you have a classical computer that do most of the job, but the quantum computer will be able to prepare some states that are not that are hard to sort of like that are hard to prepare classically and have certain interesting properties and so on. So in order to make these quantum applications work, we need to have an interface between classical computer and quantum computer. So the ability to construct an efficient classical representation of your quantum system would hence be very important in these kind of applications as well. So here are some important aspects for this task. The first is sample complexity. So as everyone may have known, if you have a quantum system and then you do some measurement on a single copy of your quantum system, you would obtain the quantum system would change due to wave function collapse. So you can no longer use that collapsed wave function to measure more properties from the original quantum system. So in principle, if you wanted to construct this classical representation, it would require you to have multiple copies of your quantum system. And sample complexity basically just measures how many copies of your quantum system do you need in order to construct this accurate classical representation. Another important aspect is quantum resource, which means when you do the quantum measurements, how complicated it is for the measurement apparatus to measure this quantum system. Do you just apply some single qubit rotation plus some basis measurements, or you do something more complicated? And of course, there are also two other important aspects, which is classical storage, meaning how big this classical representation is to represent the quantum system, as well as classical post-processing. That is, after you get the classical representation, you wanted to predict properties of the original quantum system. What is the computation time for doing that? So the standard approach for this task is known as quantum state tomography, which has been subject to a lot of studies in past decades, where the key idea is to learn the complete representation of the quantum system. So this complete representation would be a D by D matrix, where D is exponentially large in the system size. So for example, if you consider a system consisting of n qubits, then this matrix would be a size 2 to the n by 2 to the n. So it's a very large matrix. And even the sample optimal protocol, due to Zhang Wenhao et al., O'Donnell and Wright, scales exponentially in all these different aspects. So first, you need an exponential number of copies of the system. You also need to apply this exponentially long quantum circuit. You also need to have, and of course, after learning, this classical storage would scale exponentially because you're storing this exponentially large matrix. And finally, the classical post-processing time would also be exponential due to this very large metrics that you're trying to learn. So in order to circumvent this exponential scaling, there have been several recent approaches. One of the more theoretical approach is due to Scott Aronson, is known as shadow tomography, where the key philosophy is not to learn the full representation of your quantum system, but to directly predict a large number of properties given by trace of OK rho. So OKs are some observables, and these properties are given by the expectation values of these observables on the unknown quantum system rho, and you wanted to predict all of them. The best rigorous protocol was actually not due to Scott Aronson, was a very recent protocol due to Badescu and O'Donnell, where they showed that the sample complexity could be made linear in system size rather than exponential. So this D is 2 Julian. So here this is only linear in system size, and it only scales polylogarithmic with the number of properties that you wanted to predict. However, despite the number of copies that you need, it's very few. The quantum resource, the storage, and post-processing all still scales exponentially. So you need to still apply this very long circuit. You have to have a storage that's very large, exponentially large, and the post-processing time is also highly inefficient. Another very different line of research is based on machine learning, where the key idea is to perform some simple quantum measurements, and then after getting the data, you just train a neural network to represent the quantum state. So for example, one of the best known approaches called POVM neural network tomography by Huang et al., where in their protocol, you only need to apply single qubit rotation plus basis measurement. So from a quantum resource point of view, it's very, very cheap. However, all the other aspects are pretty unknown due to the black box nature of neural networks. So for example, the sample complexity is unknown, it could be exponential. The classical storage also depends on the sample complexity, so it's unknown. And the classical processing time could be long, could be short, but all of these aspects are unknown due to the lack of the general paucity of rigorous theory for neural networks. So the main question for our original work on this Nature of Physics paper is to try to combine the two reason paradigm. And we wanted to come up with a provably efficient procedure that does the following. So in step one, it learns a classical representation of this unknown quantum state from few measurements. So illustrated by the plot shown here, we called it the data acquisition phase. And then in the second step, you can use this classical representation to predict a large number of properties of the original quantum state rho. So for example, you have all these observables, O1, O2, O3, and so on. You throw it into this classical machine model, this classical model that also have the classical representation, and it would just output the expectation value of all these observables for you. So this is a hope that we wanted to achieve. We wanted to understand if it's possible that we can have such an efficient procedure that could do all these sorts of things. And in order to answer this question, in this paper, we proved the following theorem. We showed that there exists a procedure that guarantees the following. So given two constant, b and epsilon greater than 0, this procedure will learn a classical representation of an unknown quantum state rho from only b log m over epsilon squared measurements, such that subsequently, given any observables O1 to OM with some norm bounded by b, this procedure would be able to use this classical representation to predict the expectation value of all these observable up to epsilon error. So for example, suppose you wanted to be able to predict 10 to the 6 different observables, all of which has a norm bounded by 1, then naively what we have to do is we will just take each observable, measure the system. We have to actually measure them for 1 over epsilon squared number of times in order to get the expectation value up to epsilon error. And then we just repeat it for all these observables. And that would require you 10 to the 6 over epsilon squared measurements. However, this theorem shows that we actually only need 6 log 10 because b equal to 1 and log 10 to the 6 is 6 log 10. So we only need 6 log 10 over epsilon squared measurements in order to predict all of these observables accurately. And furthermore, we actually don't need to know what these observables are in advance. The procedure doesn't care about what you want to predict. You just do a set of randomized measurements, and then you will be able to predict whatever observable you want as long as its norm is bounded. And furthermore, this procedure is actually very, very simple, and it's based on randomized. So from the classical world, it's very similar to randomized projection, but in the quantum world, it's based on randomized quantum measurements. And it works as follows. So basically, we perform the following for n times. First, we randomly sample a unitary UI to rotate the quantum system. And after rotation, we just measure the system in a computational basis to obtain a bitstream BI. And we just repeat this for n times. So here is the figure. Like, we have this quantum system. We apply a random unitary, and then we just do measurements to get the computational basis, and we repeat it for multiple times. So the intuition for this is you can think of this quantum systems as an exponentially high dimensional object. Here it's illustrated by the 3-dimensional object. So every time when you do the rotation, you're basically looking at the quantum system from one angle that produces a classical snapshot from that angle. So when you randomly choose different random unitary, you will get a sense of what this high-dimensional object actually looks like. And after doing the measurement, you have to record two things. You have to record what random unitary did you apply, and what is the computational basis measurement outcome that you get. In particular, we will define this SI, which we call the classical shadow, because you're basically taking the classical shadow of a quantum object. So basically, this SI would be, we consider this state SI to be equal to UI dagger BI. So we don't really store this quantum state in your classical memory because you can't. Basically, you just store the description of this random unitary as well as the description for this computational basis BI. So here is an illustration for what this procedure is performing. So consider this row, this green points, is your quantum system. And then you're just going to do random measurements in the plus-minus basis or in the 0-1 basis. So say you measure in the plus-minus basis. It's more likely that you will get this row hat 1, this plus state, because row is closer to the plus state. So then in that case, your S1 would be equal to plus state. And suppose in your second measurement, you measure in the 0-1 basis, then it's more likely that you will get the 0 outcome because row is closer to 0. In that case, when you average across S1 and S2, you will get this state row hat 2, which is in the middle of them. And furthermore, okay, so basically when you perform the measurements for an infinite amount of times and you average over the infinite outcomes, this will actually converge to a point row hat infinity, which is just equal to the expectation value of the single shot classical shadow. And one could prove that in this setting where you measure random plus minus or random 0-1, this converged point would be equal to applying a depolarizing channel onto your quantum state row. And more formally, it's given by this, where this small n is equal to 1. And you can also write it as just applying some channel onto your quantum state row. This actually holds more generally. So you can actually consider any random ensemble for this unitary, like some distribution over the space of the unitary group. You pick some distribution, and it would always correspond to the expectation value of your classical shadow SI always corresponds to applying some CPTP map onto your unknown quantum state row. And this equality is very useful for prediction. In the prediction phase, what you do is the following. So after performing n rounds of measurements, you get S1 to Sn. How would you predict the properties of the quantum state row? Basically, what we do is we utilize this equality. We just invert it. So now you see that rho is equal to the expectation value of M inverse applied on SI, which means that for each classical shadow snapshot that you get, this SI, M inverse applied on this SI element would be approximately equal to the unknown quantum state row. So what it means is that you can just use this formula as a replacement for the original quantum state. Of course, there would be fluctuations due to statistical fluctuations due to the intrinsic measurement errors and stuff like that. But but it's fine, as we shown in our proof. And basically, if you wanted to predict the expectation value of an observable on rho, all you could do is the following. Basically, you just take the expectation value of O, like you take trace of O, apply on this M inverse SI/SY. So you just replace rho by this formula shown here. This would be a real number, or x side, so it's real. And then what you do is you perform this median of mean estimation. You chunk up all these data. For each chunk of them, you take the mean, and then you take the median of everything. And that's your prediction O hat for trace of over. And by performing statistical analysis, you can prove the following theorem. You can show that all you need to do is to perform B log M over epsilon squared measurements, and then you can predict all these observables with bounded norm up to epsilon error. So it's a very simple procedure based on randomized measurements that's actually also very powerful in practice, which we will show later. So here are two concrete examples. So the formula for this shadow norm is actually a little bit complicated, but in various cases, you can analytically analyze them very efficiently. So for example, if you consider this unitary ensemble to be this random Clifford circuit, so actually, I think David Gossett have talked about Clifford circuits in the morning talks. If you consider the unitary to be a random Clifford circuit, which would always be of at most linear depths, in that case, you can write down this channel M basically as follows. It's also a depolarizing channel, and you can upper bound this shadow norm by the Frobenius norm of your observable. So you can perform applications such as predicting quantum fidelities and so on. You can also choose a different set of ensemble. For example, you can choose this unitary to be single qubit random local Clifford circuit. So it's just a tensor product of single qubit Clifford, which you can apply it with a constant depth, which is also equivalent to performing a randomized Pauli measurement. That is, for each qubit, you just randomly measure in X, Y, or Z basis. In that case, you can also prove that the shadow norm would be upper bounded by 2 to the k times the spectral norm of O, where k is the number of qubits that this observable acts on. So it will be very efficient for estimating 2-point correlation functions or sum of local observables, such as the local Hamiltonian. So here's a summary of the theoretical results. Basically, by performing randomized measurements and constructing this classical representation, you will be able to predict a wide range of different properties, such as quantum fidelity, 2-point correlation functions, entanglement, entropy, etc., very efficiently. And let's take a look at the numerical experiment. So in this experiment, we consider the prediction of quantum fidelity. That is, in the physical lab, you have prepared some GHZ state, which is just a special type of state. And now the goal is to construct a classical representation of the state that you created such that you can predict the fidelity. Like you can estimate the fidelity with the ideal GHZ state. So in figure A, we compare it with this technique called neural network quantum state tomography based on neural networks. You can see that neural network is quite efficient, but as shown in our theorem, the number of experiments in order to predict a fidelity, a single fidelity, is actually independent of system size. In our theorem, you can see that there is no dependence on system size. There's only dependence on how many observables that you wanted to predict, as well as the norm of the observable. But since for fidelity like this, the Frobenius norm is equal to 1, you can predict a large number of them very efficiently. So as you can see, the classical shadow approach is independent of system size. So that's shown in figure A and improves upon this neural network quantum state tomography. In figure B, we consider when you have an error in your physical system. So like let's say you have some phase error in your physical system. So as the error increases, so the x-axis is the error, as the error increases, your fidelity would go down linearly. And you can see that classical shadow efficiently tracks this. However, if you apply neural network quantum state tomography, we found that it actually overestimates the fidelity. And the reason for that is it can only estimate efficiently an upper bound of the quantum fidelity. Sometimes this fidelity would be close to the true fidelity. Sometimes this estimate would be close to true fidelity, but there's no guarantee because it's more of a heuristic approach. So at least for this test case, this GHZ state case, we found that the prediction by neural network random state tomography is very off from the true value. And here is another experiment for predicting entanglement entropy. So in figure A, we consider this approximate ground state of a very well-studied physical model called the disorder Heisenberg model. And the ground state is basically a bunch of Bell pairs. And when you estimate the entanglement entropy, it should basically look exactly the same as the prediction by classical shadow. But if you use this previous approach by Bridges et al., published at Science 2019, you can see that the prediction outcome is much more noisier than the prediction by classical shadow. And similar observation can also be made in the GSG state. So you can see that classical shadow can predict orders of magnitude better than this specialized approach for estimating entanglement entropy. And here is another application where we consider the simulation of one-dimensional quantum electrodynamics. And we compared our classical shadow framework with several recent and specialized approaches. So in this application, it's performing a variational quantum simulation. So you have a stochastic optimizer for the variational parameters, which will provide with the trial state for the fermionic field. So basically in this task, what you wanted to do is you wanted to find the eigenstate of the lattice Stringer model, which is a lattice model for describing how electrons interact with one another in quantum field theory. So in the blue part, you're basically just using the stochastic optimization to propose a trial state. So just some state that you prepare with your quantum computer. And what we do here is we apply a random, like a constant depth random circuit, and then we perform measurements after the random circuit. And we perform it for several times, just like the classical shadow framework, to construct this classical representation where we will use it to predict the Hamiltonian variance. So the reason we care about Hamiltonian variance is because when it's close to zero, it means the state that you prepare is an eigenstate of your physical system. So we just do this. So we basically replace the later part where you try to measure the Hamiltonian variance. We replace it using classical shadow, and the rest remains the same. So in figure B, we consider different approaches. For example, here we compare with this handcrafted original method where they look at the form of this lattice Stringer model and try to figure out what is the best measurement scheme for that particular Hamiltonian. And it's a very powerful technique because I think there's one postdoc that just spent his time just looking at that and figuring out a very nice measurement procedure. However, you can just use this classical shadow approach, which gives you this orange line and the red line. So the orange line is a de-randomized version of the randomized classical shadow, which we'll talk a bit more in later. And you can see that using this de-randomized version, you can improve upon the number of experiments that you have to run by orders of magnitude. So in the other figure, in this figure to the right, we also compare with some other approaches, which actually is inferior compared to this handcrafted original approach. But we definitely also see improvement there as well. So that's it for the original work. And in the second part, I wanted to talk about some recent developments that extend upon our original classical shadow formalism. So the first is experimental implementation. So this construction of this protocol is with practicality in mind. And actually, you can also prove that this randomized procedure is optimal in various settings. But in our original paper, we didn't really run any physical experiments. So we only do numerical experiments. But maybe when you implement it in practice, there might be some other problems that would come up. But actually, no. So in this paper by a group of scientists in Russia, they implemented our protocol in a quantum optical experiment with high-dimensional spatial states of photons. And they showed that when you use classical shadow under very few number of measurements, it can indeed perform very accurate. It could indeed produce accurate predictions compared to some original approach, such as maximum likelihood estimate. And in the second reference, we collaborated with Peter Zoller's group in Austria to extend classical shadow framework for verifying entanglement in actual physical systems. So usually in a pure system, you can just use entanglement entropy to verify entanglement. However, in actual physical system, it's always mixed. So entanglement entropy actually doesn't work anymore, but we develop a new criteria for testing entanglement. And furthermore, and then after developing that new theory for testing entanglement, we extend this classical shadow framework for predicting if that criteria would hold and provide rigorous guarantee for the prediction performance. Another important application that's not being encompassed by our original classical shadow is quantum chemistry applications. In quantum chemistry, we wanted to measure a large number of Pauli observables that are often very high weight. That is, it acts on multiple qubits. But as you can see, actually from the brief discussion of the theory, classical shadow cannot efficiently predict high weight Pauli observables because the shadow norm is actually quite high. So how could we improve upon this? And basically, we utilize this technique called de-randomization that also appeared in this experiment. The idea is that in classical shadow formalism, you perform this randomized unitary evolution. You perform this randomized unitary, and then you do computational basis measurements. That's quite good. So it's agnostic to the properties that you wanted to predict. But in cases where you already know what are the properties that you wanted to predict, this procedure can actually be quite suboptimal. And in order to do that, in order to take what you wanted to predict into account, we utilize this technique called de-randomization, where every time you wanted to throw a coin to like choose what kind of random unitary you wanted to apply, you actually replace that randomness by the best knowledgeable choice, utilizing some cost function based on this multiplicative weight update technique. And by proposing that, by performing this de-randomization procedure, in this paper, we proved that it's guaranteed to perform equally or better than the original randomized procedure. And in a lot of cases, you can actually also show that this de-randomization approach could be substantially better than the original randomized approaches. And that's also what we see in practice. So for example, here in the figure to the right, we consider this small molecule, BH2, where we wanted to estimate the ground state energy. So we use the quantum computer to prepare the ground state, and then we wanted to estimate the ground state energy, which is a sum of a bunch of different Pauli observables. So the yellow line is our original classical shadow. As the number of experiments increases, it does start to decrease. The prediction error starts to decrease. As you can see, if you use the de-randomized version, just by performing a de-randomization of the original randomized approach, you can actually gain a very significant speed up. You can actually obtain a much, much smaller estimation error compared to the original classical shadow approach. And it also improves upon some state-of-the-art approaches, such as this LDF grouping, which is based on grouping commuting Pauli observable into groups, and then basically measure each group, basically measure all the Pauli observable in the same group simultaneously. It also improves upon this other approach from IBM Group called locally biased classical shadow. And this is not only for BES2, it also holds for all these different molecules and different types of encoding. So like JW is Jordan-Wigner encoding, P is parity encoding, and Ravi-Kitab encoding. For all of these different molecules and different encodings, we can see that by performing de-randomization, you can actually yield very significant improvement upon the original randomized approach in the quantum chemistry application. So now in the final part of the talk, I wanted to discuss this ongoing work with Richard Kuhn, Giacomo Torlai, Victor Albert, and John Presco, where we wanted to understand whether it's possible to design provably efficient machine learning algorithms for quantum many-body problems. So there have been like quantum algorithms for studying classical problems, such as what Tong-Yang has described, but there's much more lacking in rigorous machine learning algorithms for quantum problems, where we would actually most likely to see some kind of advantage. Actually, here I'm going to talk about classical ML algorithm rather than quantum ML algorithm. But ideally, if you use quantum ML, that should be more powerful than classical. But we're going to show that actually using classical ML is also very strong. So now, using classical shadow framework, we have been given the ability to represent quantum systems classically in a very efficient and accurate manner. And then it naturally raises the question of whether we can utilize this classical representation, this classical shadow framework, to train classical ML to solve challenging quantum many-body problems. For example, one of the main tasks in the study of quantum many-body physics is predicting ground states. So you have some input, some parameter that describe a physical Hamiltonian. For example, it could be a description of your molecule. It could be a description of some material, some topological matter that you try to create try to fabricate in the lab, etc. And what you wanted to do is, given parameters that describe this Hamiltonian, this physical system, you want to have a classical ML model that could predict the classical representation of the ground state. So that's one task. The second task that people have also studied is predicting phases of matter. So in this task, what you wanted to do is, suppose you have some quantum state, you represent it through this classical shadow formalism. So you have some classical representation of this quantum state. Usually it's ground state because phases of matter is defined mostly for ground states. And then what you wanted to do is you wanted to have a classical ML model that could predict which phase this quantum state is in. Is it in the trivial phase? So it's not so interesting. Or if it's in the symmetry broken phase, so it means, or if it's in the topological phase, which is the most interesting thing that people have been studying for decades now. So even though people have been studying phases of matter for a long time, many things are still unknown at the moment, especially in 2-dimension and 3-dimension. So basically, in this ongoing work, which I would just going to briefly, I would just talk briefly about, we showed that you can actually develop rigor theory that combines classical ML framework, that combines classical ML and the classical shadow formalism. In particular, for the task of predicting ground state, we proved that a classical ML model trained with data from quantum experiments can actually predict ground states more efficiently than any classical algorithm. Actually, we showed that basically what we did is we proved that for a wide range of different classes of Hamiltonians, classical ML model trained with data would be able to predict the ground state for new Hamiltonians. But if you just have a classical algorithm that could work without having this training data, then it would imply some statements that's improbable. For example, we showed that it would imply that randomized polynomial time, this complexity class RP, is equal to NP, which is highly unlikely. So by doing so, we proved that classical ML model trained with data would be able to predict ground states better than any classical algorithm. And in particular, this is just a numerical experiment for a simple Hamiltonian, but also a very physically relevant Hamiltonian, which is a Rydberg atom array that have been actively studied in the past few years. There have been a lot of Nature science paper about this Rydberg atom systems as an analog quantum simulator that allows us to study new physics and so on. So in this Rydberg atom array, this 1D Rydberg atom array, each atom is a two-level system. It's either in the ground state or it's in the Rydberg state. Rydberg state is just a highly excited state. And then these atoms are separated by some atom separation A, where its Hamiltonian is given by this formula shown here. So by tuning some of the parameters in the Hamiltonian, you actually get this phase space that consists of three different phases. One is the disordered phase, one is the Z2 ordered phase, and the third one is the V3 ordered phase. And what we do is we consider this gray circle, which are the training data. We feed this classical ML model, telling him that, oh, for this point in the phase space, in the parameter space, the ground state is that. We tell them for 20 different points, and then we wanted it to predict the ground state for these three different points. So like the star points, this diamond, and this crosses. What the machine learning model has to do is to, after given this point on this phase diagram, it has to output a ground state representation. And that's shown, and then you can use this ground state representation to predict different properties of for that ground state. For that, and that's shown in figure C. So this is for this point here. The solid line is exact computation from DMRG, which is a quite efficient procedure for one-dimensional physical system, but it doesn't really work well in 2-dimension and 3-dimension. However, since we're just trying to compare, we use this approach that could find the exact ground state. And you can see that, and the black ones, the black markers, are prediction from classical ML. And you can see that by just training on 20 data points, you can already provide a very accurate prediction performance. On the other hand, we also consider a very naive strategy. Basically, what we do is we just select the nearest training data. So among this 20 training data, which point is the closest to this point that we wanted to predict? And we just say the ground state is equal, for this testing point is equal to that training point. And if you do that, you can see that the prediction performance is very, very bad. The prediction is very off, meaning that by just utilizing 20 number of training data, classical ML could still perform very, very well. And similar situation happens for this X marker shown here, which is in the Z2 order phase. And you can see that the prediction of the classical ML model fits the true value very accurately, but when you just take the closest point, which is likely this point, the prediction performance is pretty bad. So that's for predicting ground states. In our upcoming paper, we will also showcase other physical systems, and we found all of them to perform very well, verifying and actually extending upon our theoretical predictions. And in the second application, it's predicting phases of matter. In here, we proved that under physical assumptions, classical ML models that take in the classical shadow representation could actually predict quantum phases of matter very accurately. So we provide rigorous proof for that. And here is also another numerical experiments that we perform. So here we consider this model called the bound alternating XXZ model with 2 parameters, actually 3 parameters, J prime, and also another thing called delta. And this is a phase diagram. So it consists of 3 phases, a trivial phase, a symmetry broken phase, and a very interesting topological phase. So what we do is so for example, in here, we consider delta equal to 0.5, and we just take a bunch of quantum states on that line. We construct a classical representation for those quantum states, and then we feed into this classical machine learning model, where it would perform an unsupervised clustering of all these different quantum states. And here is the 2-dimensional projection that it found. And you can easily see that it correctly classifies the trivial phase and the topological phase. And it also places the critical points at the right place, like kind of like it puts the critical points in the intermediate part of these 2 different phases. And similar things happen for delta equal to 3.0, where you have 3 different phases. You can see that this classical ML model could also classify this quantum phases of matter very accurately. So classical ML model is actually pretty strong for quantum many-body problems, but I still believe that quantum ML would be even stronger. And I've been working on some results on that as well. So to conclude, classical shadow provides a rigorous and practically efficient procedure that allows classical machines to effectively see what the quantum system is. And this procedure provides empirical advantage over various existing approaches. And finally, in this upcoming work, we demonstrate that from both analytically and numerically, classical ML plus classical shadow can effectively address various different quantum many-body problems. So that's it for my talk, and thank you so much for listening.